Hello geometry students. In this video we're going to take a look at our last lesson in Unit 6, our 6.6 notes. We're going to talk about trapezoids and kites today. So we've been talking about quadrilaterals, and specifically we've been talking about quadrilaterals that are parallelograms. So today we're going to talk about some quadrilaterals that are not parallelograms, and those are trapezoids and kites. So let's start with the trapezoid and the definition of a trapezoid. A quadrilateral is a trapezoid if and only if it has exactly one pair of parallel sides. Okay, exactly one pair of parallel sides. So that's why it is different from a parallelogram. Remember, a parallelogram has two pairs of parallel sides, but a trapezoid will only have one pair of parallel sides. Now, let's take a look at this trapezoid ABCD. We can see it has exactly one pair of parallel sides. It has four sides, so it is definitely a trapezoid. And let's identify some of the parts. Segment BC and AD, that would be the top and the bottom of this trapezoid. Those are the parallel sides. Those parallel sides are called the bases. So whenever you're looking at a trapezoid, the parallel sides we call the bases. And then the two sides that are not parallel, in this picture would be AB and CD, the non-parallel sides are always going to be called legs. And then also, as we look at a trapezoid, there are two pairs of what we call base angles. So base angles will always have one side that's a base. So that, and the pair of base angles will share that one base. So as you look at this diagram, we can see that angle A and angle D share this base AD. So one of our pair of base angles would be angle A and angle D, and then the other pair of base angles would be the pair of base angles that share side BC. So that would be angle B and angle C. Angle B and angle C. So let's take a look at this example of a trapezoid where we're being asked to find the values of x and y, and I want to see how you can use some previous knowledge to solve this problem, to find out what x and y are. Because, as you know, a trapezoid has exactly one pair of parallel sides. So let me mark those parallel sides. I'm going to highlight them yellow. Okay. The bases are parallel. Now, if we look at this one leg, we'll notice that that leg is a transversal. It intersects the two parallel lines. So whenever we have two parallel lines cut by a transversal, a type of pair of angles like these two that are on the same side of that transversal on the interior of the parallel lines, we call same side interior, or in the context of a quadrilateral, we would call those consecutive angles. So like a parallelogram, these consecutive base angles are going to be supplementary. So 20x plus 3y is the supplement of 110. So I can write the equation. I can say that 20x plus 3y is equal to 70, because 70 is the supplement of 110. But as you know, that's one equation with two unknowns. I can't find a unique solution for that. So let's go ahead and take a look at the other pair of same side interior angles. Let me highlight another transversal. Let's see, I'll make it green, I guess. So let's look at this transversal. So these two angles are on the same side of the transversal on the interior of the parallel sides, so they are also supplementary. In other words, 30x plus 6y is the supplement of 60. The supplement of 60 is 120, so I can say that 30x plus 6y is equal to 120. So that gives me a system of equations that I can solve now. Now, you can use any method you want to solve a system of equations. These are two lines. You could graph the two lines and see where they intersect. We could do substitution. But I think in this case, elimination is going to be the easiest. What I'm going to do, I'm going to choose to eliminate the y's. I notice that this this term has a coefficient of 3, and this y term has a coefficient of 6. If they both had a coefficient of 6, when I subtract the two equations, then the y's would drop out. So I'm going to rewrite this first equation so that I have a 6 here, and I can accomplish that by multiplying both sides of the equation by 2. Now, when you do this, make sure that you multiply both sides by 2. And when I do, I have a new system of equations. My new top equation is going to be 40x plus 6y now is equal to 140. And then the second equation, we just repeat that one, 30x plus 6y equals 120. So now I can subtract the two equations, and when I do, the y's are going to drop out, and I would get, let's see, 40x minus 30x is 10x. 10x is equal to 140 minus 120 is 20. So x is equal to 2. Now that I know what 2 is, I can go back and I can put 2 in either one of these equations and solve to find my y. I'm just going to go ahead and put a 2 right here. So we would have 30 times 2 plus 6y equals 120. Or 60 plus 6y equals 120, which means 6y is 60 if I divide or subtract 60 from both sides, and then y is equal to 10. So we have found our x value and we have found our y value. So I just wanted to do that little example just to remind you of what we've learned in the past about parallel lines and transversals, about supplementary angles, and also how to solve a system of equations. Okay, so let's continue our discussion of trapezoids, and we're going to talk now specifically about a trapezoid called, a special kind of trapezoid called an isosceles trapezoid. So the definition says a trapezoid is isosceles if and only if its legs, those are the non-parallel sides, if and only if its legs are congruent. So you can see here in this diagram we have a trapezoid. Well, you know what we need to label on this trapezoid? Let's go ahead and mark these bases parallel so we know for sure it's a trapezoid. Now, if we have a trapezoid with congruent legs, we would call that trapezoid an isosceles trapezoid. Now, if we're dealing with... So let's take a look at some theorems that have to do with trapezoids. And we'll be proving one of these. But let's go ahead and take a look at this first theorem. If we have a trapezoid that's an isosceles trapezoid, then we can say that each pair of base angles is congruent. Okay, so that will always be true. Our second theorem about trapezoids says the following. If we have a trapezoid with one pair of congruent base angles, then we can prove that that trapezoid is isosceles. And then the third theorem that we're going to prove this one says the following. If a trapezoid is isosceles, remember we haven't seen this symbol in a while, that means if and only if. And a trapezoid is isosceles if and only if its diagonals are congruent. So let's go ahead and prove that theorem. So the hypothesis of the theorem is that we have an isosceles trapezoid. And so we're going to assume that we have this isosceles trapezoid where AB is congruent to CD. So let's go ahead and mark that. AB congruent to CD. And what we're going to prove is that AC, which is one of the diagonals, is congruent to BD, which is the other diagonal. And the way that we will do this is by using congruent triangles. So what I'm going to do is actually take this triangle and this diagram, and I'm going to separate it into two triangles. So I have this triangle. Let me show you which triangle I am drawing. So we're going to take this triangle BAD. So let's label the label the vertices BAD. Okay, and then we're also I'm going to draw separately this triangle that I'm outlining in green. So let me redraw that one. Oops, keep picking the wrong pen. Sorry about that. Let me erase this. Okay, so let me draw the green triangle and label its vertices. That would be triangle CAD. Now, remember that side BA is congruent to CD, so let's go ahead and mark those, okay? And then to get these two triangles congruent, they share a side, so we can go ahead and mark AD congruent to itself. And then we need a third part to get these two triangles congruent. Well, let's recall that we were assuming that this is an isosceles trapezoid, and we have this theorem that says if a trapezoid is isosceles, then each pair of base angles are congruent. So that means I can mark this angle congruent to that angle. So if I write or mark those in our separate diagram. I can mark angle A congruent to angle D. So that's enough to get our two triangles congruent by side, angle, side. And once we have those two triangles congruent, we're going to be able to say that BD is congruent to CA by CPCTC. So let's get to work getting these two triangles congruent. So let's start with the fact that we're given that AB is congruent to CD. It's going to be our first step. Okay, that was what we assumed to be true. So that gives us one pair of sides congruent. And then remember we mentioned that the two triangles share a side, AD, which is congruent to itself. So it's congruent to itself by the reflexive property of congruence. Okay. And then remember, because the trapezoid is isosceles, we can say that this triangle BAD, or it's not triangle, excuse me, angle BAD, we can say that angle BAD is congruent to this angle, which would be CDA. Angle CDA. And the reason that is true is because we have a theorem that says if we have an isosceles trapezoid, we can conclude that base angles are congruent. Okay? So that gives us two pairs of sides and an angle. And when you look at the triangles that we drew separately, we can see that that angle is the included angle. So that's enough to guarantee that the triangles are congruent. So I'm going to call the yellow triangle, I'm going to call it triangle, let's see, BAD. And we're going to say that it is congruent to triangle. To get corresponding parts match up, I'm going to call the green triangle CDA. CDA. And the reason those triangles are congruent is because side angle side implies congruent triangles. Okay, so now that the triangles are congruent, notice that AC in the yellow, I'm trying to prove that AC, so that would be in the green triangle. So AC or CA in the green triangle is congruent to BD in the yellow triangle. So I can say in step 5 that segment AC is congruent to segment BD because they are corresponding parts of congruent triangles. So we'll justify that with CPCTC. Okay, the next thing we're going to look at is a definition, and that definition is the midsegment of a trapezoid. So the definition says a segment is a, oops, that's a typo. I'm so sorry. That shouldn't say median. If you could fix that, that should say mid-segment. I thought I fixed that. I apologize. Okay, a segment is the mid-segment of a trapezoid if and only if its endpoints are the midpoints of the legs. Okay, so if you would, you have a little bit of space at the bottom of your paper. If you could go ahead and draw a trapezoid. Okay, and what makes a trapezoid is the fact that it has one pair of parallel sides. And then if you would, on each of the legs, identify what appears to be the midpoint. So here's, whoops, let me grab a pen, sorry. Okay, so here's a midpoint, okay, of one leg. And then the way we are indicating that that's a midpoint is with these tick marks. Remember, a midpoint divides a segment into two congruent segments. And likewise, let's put a midpoint on the other leg. So I'll put tick marks to indicate that that point is a midpoint. Now, if I draw the segment whose endpoints are those midpoints, we have what is called a midsegment. So a segment is the midsegment of a trapezoid if and only if its endpoints are midpoints of the legs. So now let's learn a theorem that's going to be very helpful. It's called the trapezoid mid-segment theorem, and it says the following. Oops, I did it again. Would you please mark out median and change that to mid-segment? Sorry about that. I did it twice. Okay, the mid-segment of a trapezoid is parallel to the bases of the trapezoid, and its length is going to be the average of the lengths of the bases. All right, so the mid-segment theorem gives us two pieces of information. The first piece of information is if we have a mid-segment, we're going to know that that mid-segment is parallel to the bases, And secondly, we're going to know that the average, the measure of that midsegment is going to be the average of the measures of the bases. So let's use this theorem to find x and y. All right, so you'll notice that in the diagram we see tick marks here and here, which means that this is a midpoint, okay? Likewise, on the other leg, we see tick marks, which means that this is a midpoint. So that means that what we're looking at here is a midsegment. It's a segment whose endpoints are midpoints of the legs, so it's a midpoint. Okay, so the first part of the theorem tells us that a midsegment is always parallel to the bases. All right, so if we have these parallel bases, if we have this midsegment that's parallel to the base, we can look at this leg as the transversal, and as you look at these two angles, when we have parallel lines and a transversal, these two angles occupy corresponding positions. They are called corresponding angles, and as you might recall from first semester, we learned that corresponding angles are always congruent to each other. So in other words, to find x, I can set 15x equal to 75. We'll divide both sides by 15, so x is 5. All right, so we'll use the first part of the theorem to find x. We use the fact that sorry about that. We use the part that says that a midsegment is always parallel to the bases. Now to find y, let's use the second part of the theorem that says that the length of the midsegment is the average of the lengths of the bases. So how do you get an average of two lengths? You add them together and divide by 2. So if I take the lengths of the two bases, add them together and divide by 2, I know that's going to be equal to 18y. So let's go ahead and do that. Let's take 2y plus 4y plus 10. I just added together the measures of the bases. I'm going to divide that by 2 to get the average, and when I do that, the result is going to be 18y, okay? So let's just clean this up a little bit. I'm going to gather up like terms, and we get 6y plus 10 divided by 2 is equal to 18y. Now I'm going to multiply both sides by 2 to get rid of that 2 in the denominator, and I would get 6y plus 10 is equal to 36y. Subtract 6y from both sides, we get 10 is equal to 30y. Now I'm going to divide both sides by 30. Remember, we're solving for y, and y is being multiplied by 30, so we'll divide both sides by 30. So our final result is y is equal to 1/3. All right, so you'll be using that midsegment trapezoid midsegment theorem. You'll be using it quite a bit in your homework. All right, so now let's go ahead and move on and talk about our last quadrilateral, and that is we're going to talk about what a kite is. All right, so here's the definition of a kite. A quadrilateral is a kite if and only if it has two distinct pairs of congruent, so let's just use the symbol, congruent consecutive sides. All right, now let's talk about there's an important word in this definition. Let me highlight it, and that's the word distinct, okay? Now, what does the word distinct mean? You might know a set of twins, and if you know a set of twins, they might look very, very much alike, but they aren't the same person. They're two individual people. So you might look for characteristics that might distinguish one from another. So what does the word distinct mean? It just means different, okay? It means different. It's what separates one thing from another, okay? So when we, in this definition, talk about a quadrilateral as a kite, if and only if it has two distinct pairs of congruent consecutive sides, that means if I have, here's one pair of congruent consecutive sides. Now I have another distinct or different pair of congruent consecutive sides, and that would be this segment and this segment, okay? So whenever we have a quadrilateral and you see two pairs of two distinct pairs that are of consecutive congruent sides, you know you're looking at a kite. Okay, so we're going to talk about a couple of theorems that involve kites in just a second, but to do that I want you to investigate a couple things. The first thing I want you to do is I want you to sketch the diagonal KT. So let's go ahead and draw that diagonal, okay? And then I want you to answer this question. Do you think triangle KIT is congruent to triangle KET? And why or why not? Well, I hope you can see that the answer to that would be yes, because notice that already these two triangles have two pairs of congruent sides, and since they share a side, then those two triangles are going to be congruent by side, side, side. So let's say, yes, the triangles are congruent, and the reason why is because of the side, side, side that implies congruent triangles. Okay? All right, now the next thing I want you to do is I want you to sketch diagonal IE. So I'm going to do that in a different color. How about green? So let's sketch diagonal IE, and let's label the intersection of the diagonals as P. So I'm going to call that intersection P, okay? And then I want you to answer this question. Do you think triangle KPI, this little triangle here, is congruent to triangle KPE, which is this little triangle here? Well, I hope you're able to answer yes to that question. And the reason why the two triangles would be congruent is because, first of all, we know they have one pair of sides congruent. They also share a side, okay? And then also, remember a minute ago, we said that triangle KIT was congruent to triangle KET. So that means that we have a pair of congruent angles. I'm going to go ahead and mark this angle congruent to that angle. They would be congruent by CPCTC when we said that these two triangles are congruent. Okay, so that means the little triangle KIP is congruent to this little triangle, or KPI is congruent to KPE. So we're going to say yes, and the reason is because side angle side implies congruent triangles. Okay, so now let's follow up those two questions with this one. Do you suppose that the diagonals of a kite are perpendicular? Okay, so what I want to draw your attention to is a couple angles. Let's call this angle 1 and this angle 2. Okay, now I think you can tell from the diagram that 1 and 2 are definitely a linear pair of angles. Also, since we established that these two triangles are congruent, angles 1 and 2 would be corresponding parts of congruent triangle. So angles 1 and 2 are a linear pair. They are also congruent. So you might recall a theorem that we mentioned last semester, which was the following. If we have a linear pair of congruent angles, we can conclude that those angles are formed by perpendicular lines. Okay? So I think that answers our question that we just posed a minute ago, which was, are the diagonals of a kite perpendicular? Well, since angles 1 and 2 are a linear pair of congruent angles, they are formed by perpendicular lines. So I think we can answer a yes to that question as well. Okay, so that leads us to these two little theorems. The first one says, if we have a quadrilateral that's a kite, we can say that the diagonals are perpendicular to each other. And the second theorem is, if we have a quadrilateral that is a kite is always going to have exactly one pair of congruent angles. Exactly one pair of congruent angles. Okay, so I think we can tell from our little discussion up here that angle, let me see if I can get I'll grab a red color, that this angle I would be congruent to angle E, because I and E correspond, okay? So there's always going to be one pair of congruent angles, and they're going to be opposite angles in a kite. All right, so let's finish up with an example. So I want you to consider the kite, this kite PQRS, and we're given some information here. Let's see if we can find all these missing measures. Okay, I want to point something out though. When you see a number that has no unit with it, that would be the number of an angle. If you see a number with units, and that's the length of a side. So for example, QR is 5 inches, but this 4 refers to this angle. That's angle 4. And this segment is 3 inches, whereas this is angle 3 referring to that angle. Okay, so let's see if we can piece together our knowledge of kites to see if we can figure out these measures. Okay, the first thing we're asked to find is the length of PQ. Well, since this is a kite, and since kites have two pairs of consecutive congruent sides, then if QR is 5, PQ or QP is also going to be 5. All right, so this is 5 inches. Okay, the next thing we're asked to find is to find PS. Let's see, here's P and here's S. Okay, again, this is a kite. We have two distinct pairs of consecutive congruent sides. So if RS is 18, then PS is 18 inches as well. Okay, the next measure we're asked to find is QX. And QX, I want to, let me highlight a triangle. Let's take a look at this triangle. And that triangle we know to be a right triangle, because remember we had a theorem just a minute ago that says the diagonals of a kite are perpendicular. So that makes this yellow triangle a right triangle. We know that one side measures 3. We also know that the hypotenuse is 5, so I'm going to go ahead and label that. That hypotenuse was 5 inches. So we could use the Pythagorean theorem. I'm not going to take the time to do that right now, but if we were to use the Pythagorean theorem, we would see that 3 squared plus 4 squared is equal to 5 squared, so this QX has a measure of 4, okay? So maybe I should just real quick show you how I figured that out. Let's call, let me pick a variable. How about A? I'm going to call QX, I'm going to call it A. Then in that yellow triangle, we just solved this. The hypotenuse squared is equal to the sum of the squares of the two legs. That would have been 3 squared plus A squared. If you solve that for A, you're going to get 4, okay? Okay, the next measure we're going to find is the measure of angle PSR. That's this angle right here. Well, let's see. I think it would be pretty easy to prove that this triangle is congruent to this triangle by side, side, side. So this 30-degree angle would correspond to this angle 1, which is going to be 30 degrees also. 30 degrees, okay? So that means that angle PSR, if we use the angle addition postulate, would be 60 degrees. All right? And then let's talk about the measure of angle 3. Well, the measure of angle 3 is going to be 90 degrees. Remember, the diagonals of a kite are perpendicular, so the measure of angle 3 is 90 degrees. Okay? Next, let's find the measure of angle 2. Well, let's see. If 3 is 90 degrees, then this is a 90-degree angle. Okay? So in this triangle, okay, remember the acute angles of a right triangle are complementary. So if this angle is 30 degrees, angle 2 is going to be 60 degrees. Okay, so that's 60 degrees. All right. Next, we're going to find the measure of angle 4, which is this angle right here. And I think, again, it would be pretty easy to show that this yellow triangle is congruent to this white triangle. That would be easily done, which means that this 50-degree angle here corresponds to this angle. So I'm going to go ahead and label that as a 50-degree angle. And this is a right triangle, okay? So that means that this angle 4 is the complement of the 50-degree angle. So angle 4 is 40 degrees, okay? Then we're going to find the measure of angle QRS. So QRS, well, we can just use the angle addition postulate. We know that this is a 50-degree angle and this is a 60-degree angle. So QRS would be the sum of those measures. So QRS is 110 degrees. And then last but not least, let's find the measure of angle PQR. So PQR, remember we found that angle 4 a little bit ago was 40 degrees. So let me label that. So this is a 40-degree angle, okay? And we could get the two triangles congruent and to show that these two triangles congruent. So these corresponding angles would be congruent. So angle PQR would be 40 plus 40, which is 80 degrees. Okay. All right, the last thing I want to do then is just take a look at another Venn diagram. We did this the other day, but I just want to add a little bit to it. And so this outer shape would be what we call our universal set, and that would be the set of all we've been talking about convex polygons in this chapter. okay? And then we got a little more specific, and instead of talking about all polygons, we talked about those polygons that had 4 sides, and that's called a quadrilateral. So we spent quite a bit of time talking about quadrilaterals. The first type of quadrilateral we talked about, which I'm going to indicate in this oval, we talked about parallelograms, okay? And then there were some special parallelograms. Remember, if a parallelogram has 4 right angles, it's called a rectangle, okay? And if we have a parallelogram that has 4 congruent sides, that is called a rhombus. And then if we have a parallelogram that is both a rectangle and a rhombus, it has 4 right angles and 4 congruent sides, that's a very special parallelogram called a square, okay? Now, some other quadrilaterals we talked about in this lesson, we talked about trapezoids. Trapezoids. Okay, so a trapezoid, remember, has 4 sides, so it is inside this quadrilateral circle, but notice it's completely separate from the parallelogram circle because parallelograms have 2 pairs of parallel sides and a trapezoid only has 1 pair of parallel sides. And then we had a special trapezoid that had congruent legs. That was called an isosceles trapezoid, okay? And then last but not least, we talked about another quadrilateral that had 2 distinct pairs of consecutive congruent sides, and that was called a kite. Now, notice that the kite oval is completely separate from a parallelogram because kites do not have 2 pairs of parallel sides. Kites don't even have 1 pair of parallel sides. So that's why this kite circle is completely separate from the trapezoid circle. Okay, so I hope this chart helps you kind of organize all the ideas of all the different quadrilaterals that we've studied in this chapter. You'll be doing the homework or the practice problems in class when I see you next. And so if you have any questions about these notes, be sure and ask me then.